All right, good morning, everybody. So at the end of last week, we were talking about implementing a node-based stack in C. So remember, in our node-based stack, we don't have an array of elements to hold the elements of the stack. We've got these individual nodes, right? So remember, inside a node, you've got an element, and you've also got a pointer in C that points to the next node in the sequence, right? So if you push a new node, if you push a new element onto the stack, right? You end up with a new node, right? That node's next pointer points to the old top of the stack, right? And then the top of the stack now points at the current, the new node that you just pushed on top of the stack. And so we were looking at the source code for the LStack class, not LStack data structure. Right? So remember, we have a header file, right? In our header file, we've got our include guard. We've got the declaration of we have a type def which declares two things, right? So first of all, we say that there's a struct called LStack, right? And then the type def also defines the alias LStack, which we can use in place of struct LStack. Right, just like what did we do before? Our list class, or our list data structure, right? The definition of the list, the definition of the LStack struct is not in the header file, right? So again, this is another example of what's called an opaque type in C, where the user of the LStack data structure only knows that there's some structure called LStack. They don't know what's inside the structure. Right? All of the implementation details are hidden inside of the lstack.c source code file. We've got one function that returns a new empty LStack data structure. We've got a function that returns true if the stack pointed to by s is empty, false otherwise. Right? Const, because is empty should not change the state of the stack S, right? Size returns the number of elements in a stack pointed to by S, again const, because the size function should not change the state of the stack S. Pushing and popping, those do change the stack. S, so they're not const, right? Push returns a bool if you can. Push returns true if we can successfully push a new element onto the stack, false otherwise. Pop returns the element that was currently on the old top of the stack. For now, it's returning int. I don't know if we'll get to it today, either today or probably not today. So in the next class, we'll probably talk about how to implement a generic data structure in C. Right, so a stack or a list or a queue, where you can put any element you want into that data structure. So let's look at the implementation of the stack class. Right, so here's where we have our, there's our type def for our node. Right, so this is a node-based structure. Right, each node holds an element, right, and it holds a pointer to the next node. Right, so notice that it's pointer to a node. Right. So if you took CISC220 last term, this is just like the structure. This is just like the linked stack data structure that we implemented in CISC220, except now you've got, instead of using a reference to the next node, you've got a pointer to the next node. Right. The stack structure itself simply consists of a pointer to the top node. That pointer will be null if the stack is empty. Right. And then we have the size of the stack. Right. So that's just the number of elements in the stack. To make a new stack, so this would be like our default constructor in Java. Right. This makes an empty new stack, returns the pointer to that stack. So right, Control Z, returns a pointer to the stack back to the caller. Right. So we dynamically allocate space for the stack structure. Right. If the allocation fails, return null, indicating we couldn't make there wasn't enough memory to make a new stack. Right. It's an empty stack, so the top of the stack is null, right? And size is 0, right? If we want to know if a stack is empty, we simply look at the size of the stack, right? So if the size of the stack is 0, it's empty, right? If it's not 0, then it's not empty. To get the size of the stack, just return the size member of the stack structure. And so the only interesting functions in here are push and pop. Right? So when we push an element onto the stack, right, you need to make a new node to store the element. Right? So the very first thing you do is dynamically allocate space for a new node. Right? Now remember, when you dynamically allocate space, right, at some point you're going to have to deallocate that space. Right? Otherwise you end up with a memory leak. So somewhere in this stack implementation, we're going to have to free that node that we just allocated. So if we fail, if malloc fails, return false, indicating that we've run out of memory, can't actually push, and can't push the new element onto the stack. Right? If malloc succeeds, then it's straightforward. Right? We've got this new node, so we just fill in the fields of the new node, right, or the members of the new node. Right? So what do we store in the node? Well, we store elem, right? So n-elem equals lm, right? So that line there takes our new node and it sets its next link to point to the current top of the stack. Right? So you want to push the element onto the top of the stack. Right. Whoops. So that's the current top node. You're going to push a new element onto the top of the stack, so that's n. Right? And you want to set n next to point to top. Right? So that's n next. Right? Like that. Right? So you make that point to the top of the stack. You then want to adjust the top of the stack so it points at n. Right? So s top gets assigned the value n. Right? And then increase the size of the stack by 1. Right? That's very easy to forget to do. Don't forget to do it because you've added a new element to the stack. Right? If you forget to do that, then your size member is set incorrectly. And then finally return true, indicating that we've successfully pushed an element onto the stack. Now what about popping an element from the stack? So when you pop an element from the stack, that's one place when we're going to free the memory that was allocated to the node. Right? So when you pop an element from the stack, you want to get rid of that node. Right? So this would be an appropriate place to free the memory that's allocated to the node. So in pop, the last thing we're going to do is we're going to free the old top of the stack. Okay? So in pop, the first thing you do is you get a pointer to the top of the stack. Right? Now I need that pointer because I need to return the, oh hey, there's a mistake here. Return elem. There we go. That's the really weird part in C. So that return statement was missing, but if you compile the source code file, it actually works. It doesn't actually return anything because the return statement's missing. I think what gets returned is 0 in this case. But the fact that the return statement's missing and it still compiles is very strange to me. But that's the way the language works. So you have to watch out for that. All right, so the first thing we do is we get a pointer to the old top of the stack, right? And the reason I need this is because I need to return the element that was sitting there, right? Sorry, I need to deallocate that node at the end, right? So grab the element that's currently sitting at the top of the stack, because I need to return that later on down here, right? Now all I do is I just adjust the top of the stack, right? So how do I move the top of the stack to the next node? Well, I just follow top next. Right? And that takes you to the next node that's on the stack. Right? So s top equals top next, decrease the size of the stack by 1. Right? Now we free the old top of the stack. Right? So this is one of the places where it's appropriate to free the memory that was allocated to that node. Right? Because you no longer need the memory associated with that node. So this would be a good place to free that. That's a good place to free that memory. Right, so that free statement there deallocates the memory that was allocated here. Right? And then finally at the end return the element. The last function that we need to implement is a function that frees all of the memory associated with a stack. Right? So it's possible that someone uses a stack data structure, they push a bunch of elements onto the stack, but they don't pop everything else off. Right? So if they don't pop everything off, there's a bunch of memory allocated to the nodes storing those elements. So if you need to, to free a stack, right, you need to free all of its nodes. Right? You also need to free the stack structure. Right? So I need to free the memory that's allocated to hold the size and the top node of the structure. Right? So to free all the nodes, you just walk along all of the nodes. Right? So this is the standard follow all the nodes until you get to the end of the sequence loop. Right? So you start with a pointer to the top node. Right? While that pointer is not null, right, you know that there's a node that you can do something with. Right? In this case, I want to get rid of that node. Right? So I want to walk along the sequence of nodes. Right? I want to free this node n, but I can't free it yet because I still need its next link. Right? So I remember what the next node is in the sequence. Right? Free the node. Right? So now free all the memory associated with that node. So that free there frees the memory that was allocated here. Right? And then move n to the next node in the sequence. Right? So that right there is the, so if you ignore that line and that line there, right? That loop there is the standard way to walk along a linear sequence of nodes. Right? Start at the top node. While that node's not null, do something with the node, and then advance the node to the next node. Right? You could also write, if we didn't free n here, you would write n equals n next. Right? But because we freed the node, we have to write that instead. All right? And that's the implementation, that's the bare bones implementation of the a linked stack data structure. Right? Now, of course, you can add more functions if you want. Right? So let's just quickly, here we go. Right? So for example, you can print or you can generate the string representation of a stack. Right? So if you wanted to print a stack, what do you have to do? Well, I have to iterate over the sequence of nodes. Right? And so the general iteration pattern is as follows. So this is exactly the same as I just showed you a second ago. Right? You start out with a node, a pointer to a node that points at some starting node, usually the top node. Right? While that node's not null, right, do something with the node there, then advance the node. Right? So n equals n next. Right? Now, whatever you do at the end of this loop, right, don't dereference n here. Right? So don't try to use n next, or n elem, right? Because at this point here, n is null. Right? By the time you because the loop condition is that while n is not null. Right? So at the end of the loop, n is null. Don't dereference the node. Don't try to dereference n there. Right? And that's the general pattern for walking along a sequence of nodes. You can make modifications to this general pattern. So let me just edit this slide instead of typing it out in an editor. So for example, sometimes you need two nodes. You need two nodes when you're walking along a sequence for some reason, right? So for example, node star m equals, we'll start out with null, right? So now I'm going to keep track of two pointers to nodes inside of a sequence. I'm going to walk along, I'm going to walk m and n along the sequence, right? M equals n, and then n equals n next, right? Down here, m is points to the last node. Right? So some algorithms need to look at two consecutive nodes in the sequence. Right? So you need to look at the first and the second, then the second and the third, and the third and the fourth, and so on and so on. Right? And so the trick here is you just make two pointers, right? Where m points to the node that's before n, right? So m starts as null, n starts at the top node, I guess, right? While n's not null, right? You just you do something with m and n here, right? And then advance both pointers here, right? So m moves to the next node, which is pointed at by n, right? And then n points to the next node, which is pointed at by n next. right? And then when you end up at the bottom here, you're guaranteed that m points at the last node in the sequence, assuming that last node actually exists. Right? And so this type of pattern here would be useful if you wanted to check if a sequence was sorted, for example. Right? So if you want to check if a sequence is sorted, you need to compare the two elements pointed at, the two elements stored in the nodes pointed at by m and n. Right? And that's how you do it there. Some algorithms will take three nodes, 3 pointers. Right? If you need to look at 3 consecutive elements, right? Some will take 4. That would be unusual. 2 is not unusual though. And so that's the trick you can play with pointers, right? And so if you want a picture of what this looks like, right, we start out with n. So n's just my node, pointer to a node, points at the top element in the stack, right? To advance n, you just follow its next link, right? So n points at this node's next link points at the next node. So that node dot next takes you to the next node in the sequence, right? And similarly there. Right? And one more time, right? So we follow its link, and now it's a null, right? So when n points to null, the loop doesn't run, right? And so it stops. If you were to draw m in this sequence as well, then m's on top of n, right? So m always points to the node in front of n, and so you'd see that m points to the last node in the sequence. Right? If you wanted to print a stack, then you can just use this general iteration pattern. Right? So we'll start out by printing the string top, then comma and space. Right? We'll get our pointer to a node and set it to point to the top node of the stack. Right? While that node is not null, print out the element followed by a comma, followed by a space. Right? So the element is just the element stored in the current node. Right? Move to the next node. Right? When you're done the loop, you know you visited every element in the sequence, right? And now I can print out the bottom, I can print out the string bottom, right? So this prints out top, element, 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 bottom, right? So that's the way it prints. That's how I decided to implement the print function for a stack. You might choose to implement it some other way, right? So you might print top, then element, 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 bottom, if you wanted to, right? Okay. That node structure, if you look at it, right? So you've got a structure, right? A node. Inside that structure, there's a pointer to another node, right? And so that's the classic example of structural recursion, right? So anytime you've got one of these node-based structures, it's the structure of the thing that you're implementing is recursive, right? Every node has a pointer to a node, right? That node has a pointer to a node. That node has a pointer to a node, and so on, and so on, and so on. Right? Another way to look at this is that you can think of a node, any node in a stack, you can think of that as being the top node of some other stack. Right? So here we've got 3 nodes in our stack. Right? The 3, that's the top node. Right? But if you look at the 2, right, that 2 is the top node of the stack of size 2. Right? And that 1, that's the top node of a stack of size 1. Right? So in other words, every time you move down a node in the stack, right, you can view that next node as being the node, as being the top of a stack that's 1 smaller than the previous stack. Right? And that makes, and so by now, for most of you, right, you're all in 2nd or 3rd year now, or 4th year, I guess, possibly, right? Right away, this should be ringing. You should be thinking, oh, this is just recursion, right? So anytime you've got one of these node-based structures, recursive algorithms become well, they become relatively easy to implement, right? If you want to take CISC235, the data structures course, when you start to implement binary trees or graphs, you'll do so using a node-based structure. A lot of the algorithms that work on binary trees or graphs are much easier to implement recursively than they are to implement iteratively. Right? So as soon as you have a node that points at 2 different things, right, it starts to become harder to implement that, implement those functions using iteration. Right? Because you have to remember, I have to visit this node's left node and its right node. Right? When you visit this node's left node, you have to remember I have to go to the left and the right, right? And so on and so on and so on. So we can convert the print function into a recursive function. Right? So there's my print function. So we start out by printing the string top, right? And now I call a recursive function to actually print out all of the elements of the stack. Right? So print rec is the recursive version of print that only prints out the elements. It doesn't print out the top or the string top or the string bottom. Right? So the recursive function print rec takes in a node n. Right? So, and it's going to start by taking in the top node. Right? So this function is going to be recursive, which means it needs a base case. Right? So in other words, when do I know that I'm done printing a stack? Right? Well, you know you're done when there's nothing left to print. Right? When do you know there's nothing left to print? When that node is null. Right? So if that node is null, return. Right? You're done. You don't have to print out anything. Right? Otherwise, you know there's stuff to print. Right? I need to print out this node, and then I need to print out the rest of the nodes. Right? So print out the node. Right? Now how do I print out the rest of the nodes? I just call the recursive function, because that's what it does. Right? The recursive function prints out the nodes in a stack. Right? What is the rest of the stack? Well, it's the stack starting at the next node. Right? Why is this true? Because the structure is recursive. Right? And so that you can easily convert the iterative version of print into a recursive version of print. Right? You wouldn't actually want to in this case. The iterative version just is probably easier to write. Right? But as soon as you start working with trees and graphs, you'll begin to appreciate you'll begin to appreciate the power of recursion. Right? For these linear structures, it's not so useful. All right, any questions about this linked stack-based data structure that we've implemented? All right. Okay, so then I guess the next thing we can look at is a linked-based queue, which is very similar to a linked-based stack. Right, so where's... All right, so you can implement a queue in many ways, right? So you can use an array, and then you get an array-based queue, right? Turns out an array-based queue is a little tricky to implement. I don't remember, so if you took CISC220 with me last term, you might have seen it, but I don't remember if we did it or not. If you took it from me with me the year before, then we definitely didn't do it. I don't think we did it. Turns out it's actually a little easier to implement with linked nodes if you want to implement a queue. So a queue, that's an example of a queue. Right? There's a front of the queue, there's a back of the queue, right? You get into the queue at the back, you come out of the queue at the front. Right? So there's this notion of the front and the back of the queue. Right? Notice the pointers to the front and back of the queue. Right? Now a queue like a stack classically only supports two operations. Right? So I can enqueue, which puts a new element at the back of the queue. Right? Or you can dequeue, which removes the element at the front of the queue. Right? You can implement other operations if you wanted to, right? So how many elements are in the queue? Is the queue empty? Look at the front element of the queue, but don't take it out, right? You might implement contains, right? So does a queue contain a particular element? And so on and so on and so forth. Right? The enqueue operation looks as follows, right? So if you have an empty queue, right? Then this thing F, that's the pointer to the front element of the queue. B is the pointer to the back element of the queue. Right? In an empty queue, these both point nowhere, right? So they're both null. If you enqueue a single element, though, the front and the back, they both point to the same element. Right? So the front of the queue is the A, and so is the back of the queue. Right? If you enqueue the B, right? So you add the B to the end of the sequence, right? And then adjust the back pointer. Right? Front pointer doesn't normally move. Right? Enqueue the C, so add the C to the back of the queue, adjust the back pointer, and so on, and so on. Right? Now to dequeue, you're going to take that element out, right? So I'm going to return the E. So remember what the E is, so I can return it at the end of the function, and then adjust the back pointer. Right? So to dequeue the E, right? So that string's going to be equal. Oh wait, sorry, haha, wrong way. Sorry, I was thinking of a stack. Let me back up there. Okay, so to DQ, you're going to take the element out at the front and then adjust the front pointer. Sorry. Okay, so I'm going to DQ the A, so the A comes out, and then the front pointer moves to the B. Now in the picture, in the picture I'm shifting all the elements forward, right? But in reality, when you're using a node-based structure, you're just going to move this front, you're going to move the front pointer, right? All we're going to do is move the front pointer to move to the next element in the sequence, right? So to DQ the B, right, where the B is going to come out, and then we're going to move the front pointer to point at the C. Right. To DQ the C, you're going to remove the element, right, and then move the front pointer down the sequence, right, and then so on and so on. Right? So when you DQ the last element, right, that's where the front and the back pointer both change. Right? So normally when you DQ, you're only adjusting the front pointer. Right? If you DQ the last element of the sequence, you have to adjust both pointers, right? Because the back pointer no longer points at anything. So that's one of the special cases that you have to deal with. Right? So queues are what are called FIFO data structures, right? First in, first out. So the first person in line is the first person to come out of the line. Right? And they're widely used in computer science and in computer engineering. Right? So commonplace, so online, so any web server has a queue of some kind, right? There are requests for a web page. Those all get stuck into a queue. The server serves up the requests one at a time. Right? If you're buying tickets on Ticketmaster or something like that, right, your request goes into a queue to make sure that they don't sell too many tickets. Right? Same with airplane tickets and things like that. Right? All of these things are queue-based. Right? Amazon's got giant queues all over the place. In your operating systems, there are a whole bunch of queues, right? Because operating systems are basically, they're supposed to serve up or supposed to provide services to clients. Right? So CPU, you consider that as a service, right? You can only, a simple picture of a CPU is you can only run one process on the CPU at one time, at any time, right? If you have a bunch of processes, you have to give each process some time on the CPU, right? So the processes all go into a queue, right? You might have a bunch of people trying to access a printer, all of those requests go into a queue, right? Same with your disk, same with the network, same with anything else on your computer, right? The operating system has queues for all of these services. Breadth first search is an example of a queue. There's actually a whole branch of mathematics devoted to queuing theory, believe it or not. Right. Here's an example of using a queue in a robotics problem. So in robotics, there's one of the fundamental problems in robotics is what's called the path planning problem. Right? You've got a robot somewhere in the world, it needs to reach a destination of some kind. Right? The robot has a map, it needs to find a path to go from the starting location to the destination. Right? It turns out that the way a lot of these maps are stored, they're just rectangular grids. Right? So for example, that's a map, that's a simple map of a simple world. Right? So we've got a relatively small grid. Anything in red is an obstacle. Anything in white is free space, so that's where the robot can travel. Right? The robot might know that it's here, right? And it might know that it wants to get here. Right? So I guess a real life example of this is on your GPS system, your GPS knows where you are right now. You type in where you want to go, it tries to find a path from the goal to the start. Right? That's a more complicated problem because it needs to only drive on roads. Right? Okay, so there's something called the Wavefront Planner. And so the way the Wavefront Planner works is you have this grid-like world. Right? Anything that's any location where the robot can move to, you mark it with a 0. Right? So you just mark that grid location with a 0. Anywhere the robot cannot move to, you mark it with a 1. Right? So all the red squares get marked with a 1. Right? Your goal. The goal. Do I have this right? Oh, sorry. The goal is here and the start's here. I have it backwards, right? So your starting location here, the goal location's here. You mark the goal location with a 2. And the start location gets some special symbol. Right? And so the way the Wavefront Planner works is as follows. Right? So starting at label number 2, right? As long as that starting cell is unlabeled, right? So as long as that cell there, right, is unlabeled, for every cell C that has the label L, right, so has the value 2, right, you just look at the cells connected to that cell that have the label 0, right? So in other words, you look at the cells connected to the current location where you haven't considered moving to yet, right? And you just label that potential cell with the value L plus 1, and you just keep on going, right? So that 2, right, I mark all of its adjacent locations that haven't been visited yet, right, so have the value 0 with a 3, and now you repeat the process, right? So for each 3, I'm going to mark its adjacent zeros with 4. Right? For each 4, I'm going to mark the adjacent locations with 5, and so on. Right? So eventually you get to here. Right? For each 14, I'm going to mark the adjacent locations with 15. So that'll get 15, that'll get 15. Right? And now for this cell, that's 15, so I'm going to mark that with a 15. Right? And now for this cell, that's 15, so I'll only mark that with a 15. Right? And you just keep on going. Right? And notice how this thing works, right? So notice that the, I guess the front of the cells, they just keep on expanding outwards, right? And eventually, you end up at this situation here, right? So eventually I end up marking these 3 cells with a 49, the next, and then I'll end up marking the starting cell with a 50 on the next iteration of the algorithm, right? So that gets marked with a 50. That'll be a 50, that'll be a 50, that'll be a 50. Right? And now to generate the path, you just go backwards. Right? So starting at the 50, right, while you haven't reached the goal condition, just move to any cell that has the number 49. Right? And then 48, and then 47, and then 46. Right? So for example, starting at the 50, go to any cell marked 49. So I'm going to go here. Right? Then to any cell marked 48, and then 47, 46, right? At any point, it doesn't matter which choice you make, right? If I choose to go to 45 up here, then I'm just going to go like this, so it doesn't matter. Right? So now you just count down until you reach the goal location, right? And there's your planned path. Right? So this is one of the earliest robotics planning algorithms, right? So this was done a long time ago. If you've done data structures before, or if you, does anybody recognize what this thing is? What it's actually doing? Okay, so this is actually doing something you'll learn about in data structures, right? But keep that in mind when you take your data structures course, right? That's actually just a classic computer science algorithm dressed up as a robotics problem. So what does the Q class or the Q data structure looks like? Well, it looks exactly like the stack data structure, right? It's almost like line for line identical, right? So there's your structure. Right? There's the declaration of the structure. So I'm going to make this thing called LQ. Right? There's your quote unquote no argument constructor. Right? Makes an empty queue. Right? There's is empty. There's size. Right? They work exactly the same way as the stack functions. There's NQ and DQ. Right? There's free and there's print. Right? So almost exactly the same as a stack. The only difference, or the main difference, is in our queue structure itself, right? So because in a queue, you're doing things at both ends of the queue, you need pointers to the nodes at the front and the back of the queue, right? So now we've got this extra field here called back, right? Front you can think of as just being the top of the queue if you want, right? It doesn't actually matter. Or back, you can think of the back as being the top of the queue. Yeah, right? The node is exactly the same. Right? A node just stores an element and the next node in the sequence. Right? Making an empty queue is exactly the same thing as making an empty stack, except you also set the back of the queue to point to null. Right? Otherwise, it's exactly the same. Right? Is empty size exactly the same. Right? NQ is where things get slightly tricky. Right? So the beginning of NQ is the same as push, right? Allocate space for a new node, right? Fill in the members of the node structure, right? So store the element in the node, right? And next, we're going to start by making that point to null. But we're going to, that's right. So we're going to make that point to null, right? Because this is the back element of the, we're going to put this node at the end of the queue, right? So there is no next element after this one, right? So that's a little bit different than in a stack, right? In a stack, we set the next to point to the top, right? In a queue, because we're adding the node at the end, it points to null, right? Now I've got this special case, right? If the queue is empty, right? So remember how the queue works, right? So in a non-empty queue, right, we've got our pointer to the front of the queue, right? When you add or enqueue an element, normally you only have to do something at the back, right? So when I enqueue an element, I'm going to enqueue this element because I'm out of space, right? So when I enqueue this element, back was here, right? So I'm going to add that element to the back of the queue, and then I'm going to adjust back to point to the new node, right? Normally you don't have to touch the front pointer, right? But if the stack is empty, or if the queue is empty, right, that's the one time I have to adjust the front of the queue, right? So when the queue is empty, I have to make the front pointer point to the new node, right? Otherwise, normally I don't have to adjust the front pointer. Right? If the queue is not empty, then I want to add the node to the end of the sequence, right? So in other words, right, I want to go to the back of the queue. I've got a pointer to that, right? I want to say that that node now points to the new node, right? Or that node's next link points to the new node, right? So queue back next is now equal to n, right? So that joins n to the end of the node n to the end of the sequence, right? Now you adjust the back of the queue, right? And increase the size of the queue by 1, right? So when you do things to both ends of a sequence, you're going to run into a bunch of special cases, right? And this is also going to be the case if you try to implement a linked list, right? Because in a linked list, you can remove something from the front or you can add something to the back, right? So you're doing things at both ends of the list. DQ is going to be similar, right? So DQ is going to be a lot like pop in a stack, except there's probably going to be a special case. Right? So everything happens at the front when you dequeue. So I'm going to get a pointer to the current front of the queue. Right? I'm going to store a pointer to the current front of the queue because I need to free that node when I'm done with dequeuing. Right? So there's my pointer to the current front. At the end, right, I'm going to free that front node. Right? I need to free that front node because I allocated space for that node at some point when I enqueued it. I'm going to get the element that's in the current front of the node because I need to return that element at the end of the function. Right? Now I'm going to dequeue the element, and so the way I'm going to do that is I'm going to try to move front to the next element in the sequence. Right? So normally when you dequeue, you're only touching front, right? But there's going to be a special case when you have to touch back. Right? So what's the special case? So the special case occurs when there's only one element in the queue, right? Because if there's one element in the queue and I get rid of it, right, then the back of the queue now points to null, right? So if the size of the queue is 1, make the back pointer point to null because that node is going to disappear, right? Adjust the front node, right? So queue front equals front next. Right? This also works if the queue size is 1, right? Because the queue size is 1, front next is null, right? So this is fine. Decrease the size of the queue by 1, right? So again, watch out for that special case, right? It's very easy to miss this special case. If you don't write a unit test for this, you almost certainly won't catch it, right? And that's it. So slightly more complicated than popping an element from a stack. Right? Because you have to deal with the special case. Freeing a queue is exactly the same as freeing a stack. Right? You're going to walk along the sequence of nodes, deallocating nodes as you go. right? And then at the end, you'll free the memory that's allocated to the queue structure itself. Right? So very similar to a stack. You just have to deal with a couple of special cases in queue and dequeue. Any questions? All right. So that's that's linked-based queues. And what are we at? 10 after. I just want to look at what the next topic is before deciding if I want to keep on going. Not that. Not that either. You do. There is another assignment coming out today, by the way. It's actually ready. I should have posted it yesterday. So what is the next lecture? The next, generic collections. Let me just take a peek at what's in here and to see if it's worth starting or not. Okay, so what do we do? Okay, so it's worth doing a few slides, and then we'll end, I guess, at about 15 after. All right, so everything we've done so far is we've created data structures that can hold only a single element type, which is inconvenient, right? So we've got a list of ints. We've got a stack of, I think everything's int, right? Everything's been int so far. If you want to store something else in these collections, you've got two choices, right? Choice number one is you make another data structure for the new element type. Right? So if I want a stack of double, right, I basically repeat everything that's in the stack data structure, except I change the element type to double. Right? If you do that, you also have to change the name of the structure, and you have to change all the function names. Because if you don't, you can't use an int-based stack and a double-based stack in the same program at the same time. Right? So that's kind of inconvenient. Right? You now have something called LStack int and LStack double, which is going to suck. Right? It's really going to suck, right? You're also going to have a bunch of duplicated code all over the place. So your choice, the alternative then is to create a data structure where you can actually store whatever you want in the data structure. Right? So if you want to make, for example, a type-safe list of strings, so like I said, the alternative number one is to make a new list implementation that stores strings. Right? And this involves a lot of manual copying and code duplication, which you never want to do. Right? Now, surprisingly, the language C++, right, it has a facility called templates, designed especially for this. Right? So in C++, you make a data structure, you call it a generic data structure using this template mechanism. Right? What the compiler actually does when you make, so if you make for example, a stack of int using C++, then what the compiler actually does is it takes your data structure and produces a special, it produces code explicitly for a stack of int. Right? If you then make a stack of double, the compiler takes your code for your template and makes code specifically for a stack of double. Right? So in other words, C++ automates this manual copying and code duplication in its template mechanism. Right? In Java, generics work completely differently. Right? So in Java, when you make a generic data structure, there's only one instance there's only one version of that data structure. Right? So in other words, if you make a list of int, right? That's the same thing. The representation is the same as making a list of double or a list of string or a list of anything else. Right? So in other words, the compiler does not make separate list classes for all of your different element types. Right? In C++, the template mechanism is actually a lot more sophisticated than just copying code and than just automatically copying and duplicating code. In C++, the template language is actually its own language. So you can actually do something called template metaprogramming. You can program in C++ using the template mechanism, which is very bizarre. Okay, now how are we going to do this in C? Right? So how am I going to make a generic data structure in C? Right? Because in C, there's no type that can represent any object, right? In Java, you've got the type big O object, right? Big O object can represent anything in the Java language, right? The closest thing we have in C is a pointer to void, right? So remember what a pointer to void can store. Remember what a pointer to void can point at, right? Pointer to void can point to any object type, right? And so this is going to be the trick that we're going to use to implement a generic data structure, right? So what we're going to do is we're going to implement a generic collection where our element type is a pointer to void, right? So in other words, inside of a node, or we're going to make an array in an array-based list, for example, right? We're going to store void pointers, right? Those pointers point out to elements, point out to the individual elements, right? Those elements are going to be stored. Those elements will be stored somewhere in memory. Right? Now, this is a little bit different than what happens in Java, right? So in Java, if you make a list of string, you can only put strings into the list, right? Because a void pointer can point at anything, in our generic C collections, we're able to have mixed types in the collections, right? So we can make a list, and then we can put an int in it, and a double, and a string, and then whatever you want, right? Another list, right? You can put whatever you want into the list or stack or queue, and that's closer to how it works in Python. Right? So in Python, you probably, whoever taught you Python, probably had you doing wacky stuff like putting in a string representing a name for a student, and then beside that you put in a number representing the grade for an assignment or something crazy like that. Right? So just like in Python, we're going to lose all sense of type safety. Right? And when we make a list of something, it could be a list of anything. Right? The elements could have any type. So the programmer is now going to be responsible for remembering what types are stored in the collection, right? Which is very different than how Java works, right? Java, the language, tries very hard to ensure type safety. All right, so what's this going to end up looking like? So for our node-based structures, we're going to change the definition of a node, right? The only thing that changes, though, is that our element type is no longer just int or something else, right? Now our element type is a pointer to void, okay? Otherwise, everything else is going to stay the same, right? So some functions don't change, right? So initializing a stack, nothing changes, right? Checking if a stack is empty, nothing changes, right? Getting the size of the stack, nothing changes. So the only things that are going to change are push and pop, right? And we have to make some small modifications to their function declarations. Right? So to push an element onto a stack, right, we're no longer pushing an int elem onto the stack. We're going to push an elem that's pointed to by a void pointer. Right? When we pop an element from the stack, we're no longer returning an int. Right? We're going to return a void pointer, right, to the element. Right? Now, the problem here is that the caller needs to remember what they pushed onto the stack, right? Because all they're getting back is a void pointer, right? To actually use the thing that they're getting back, they have to cast that pointer to their element type. Right? And so I guess in the next lecture, which I guess is tomorrow, we'll implement these methods in C and see how this data structure actually works. All right? So we'll stop things there, and I'll see you tomorrow.